Welcome back, inspectors. Today we are covering one of the most powerful inspection methods used in modern oil and gas facilities, magnetic flux leakage testing, or simply MFL. Now pay very close attention here. Most inspectors know magnetic particle testing. They understand visual particle accumulation around defects. But very few truly understand how MFL detects discontinuities electronically, without using visible particles. And this difference matters. Why? Because MFL is everywhere in industry. Imagine you are working during a major refinery shutdown. You are assigned to inspect a massive crude oil storage tank floor. The client wants fast scanning, accurate corrosion mapping, and permanent digital records. Can MT do that efficiently? No. Can UT scan an entire tank floor quickly? Difficult. That is where MFL becomes a game changer. This method is widely used for storage tank floor inspection, pipeline pigging, wire rope inspection, pressure vessel corrosion screening. This question appears repeatedly in certification exams. Where is MFL most commonly used? Remember tank floors and corrosion detection. By the end of this chapter, you will understand not just theory, but real field application. Let's move into the learning objectives. Before learning any NDT method, you need to know exactly what must be mastered. In this chapter, we will focus on 7 major areas. First, the basic physics behind MFL. Second, how MFL differs from MT and eddy current testing. This is where many inspectors get confused. Many Level II candidates answer this incorrectly. They assume MFL belongs under MT because both use magnetization. Wrong. Historically, MFL was actually classified under eddy current testing because of the sensor technology, not because of magnetization. That's a classic ASNT trap. Third, we will study flux leakage. Fourth, sensors. You must clearly distinguish between search coils, Hall effect sensors. Exam tip. If the exam asks, which MFL sensor requires movement to generate signal? Answer immediately. Search coil. If the sensor detects static magnetic fields? Hall effect sensor. Remember this because it can save you easy marks in the exam. Finally, we will study equipment, signal quality, applications, and mock questions. Now let's begin with the origin of MFL. So what exactly is magnetic flux leakage testing? In simple language, we magnetize a ferromagnetic object. If there is corrosion, pitting, cracking, or metal loss, magnetic flux leaks from the defect region. Sensors detect that leakage. That electronic signal tells us where the discontinuity exists. Now let me show you how this works in the real field. Suppose you are inspecting a large storage tank bottom plate. The floor plate may have underside corrosion caused by moisture trapped between the plate and foundation. You cannot see the corrosion externally. But when you magnetize the plate, metal loss disturbs magnetic flow. That disturbance creates leakage. The sensor detects it. That is MFL. Now a very important historical point. MFL was pioneered in the 1930s by Elmer Sperry. This question appears repeatedly in certification exams. Who pioneered early MFL? Answer. Elmer Sperry. Another major exam trap. MFL was originally classified under A. MT, B. UT, C. ET, D. RT. Correct answer. ET, eddy current testing. Not MT. Don't memorize this. Understand it. It was classified under ET because the electromagnetic sensor was considered the primary distinguishing feature. Now let's move into magnetism fundamentals. To understand MFL, you must first understand magnetism. Here is the foundation. MFL works only on ferromagnetic materials. I repeat. Only ferromagnetic materials. That includes iron, steel, cobalt, nickel, some 400 series stainless steels. Can we inspect aluminum with MFL? No. Copper? No. Titanium? No. 300 series stainless steel? No. This question appears repeatedly in certification exams. Many candidates choose magnetic metals instead of ferromagnetic metals. That wording difference matters. Now pay close attention to magnetic lines of force. 3 rules. Rule 1. Lines never cross. Rule 2. Lines never break. Rule 3. Lines never merge. This is extremely important during refinery shutdown inspections because these rules explain defect detection. If lines do not break, then how do we detect defects? Answer. They distort around discontinuities. That distortion is the leakage field. That is the entire physics of MFL. Simple, but extremely important. Next, let's see exactly how leakage forms. This slide contains the core physics of MFL. Imagine magnetic flux like water flowing through a pipeline. Now suppose corrosion creates a hole in that pipe. What happens? Water leaks out. Magnetic flux behaves similarly. When metal is continuous, flux flows smoothly. But when a crack, pit, or void appears, the magnetic path is interrupted. The defect behaves like an air gap. Air has very low permeability. So the magnetic field resists traveling through air. Instead, flux bulges outward. That outward bulging is called flux leakage. Sensors positioned above the surface detect this leakage. Now here is a critical exam question. As discontinuity depth increases, what happens to leakage strength? Answer. Leakage signal decreases. Why? Because surrounding metal smooths the field. Think carefully. A surface crack creates strong leakage. A deep internal defect creates weak leakage. Most inspectors know the theory, but very few understand the practical application. In field inspection, shallow corrosion is easier to detect than deep buried flaws. This is why defect depth matters greatly in MFL sensitivity. Next slide will visualize this beautifully. Now let's compare surface and subsurface defects visually. On the left, imagine a surface crack. The defect opens directly to air. Magnetic flux sees a strong interruption. A large leakage field forms above the surface. Result? Strong signal. Easy detection. Now the right side. Suppose the defect is buried deeper inside steel. What happens? The surrounding metal partially carries the magnetic field. That smooths the distortion. Only a small leakage field reaches the sensor. Result? Weak signal. Hard detection. Here's a common mistake I see on site. Junior inspectors assume larger defect always means larger signal. Not necessarily. Depth matters. Orientation matters. Sensor distance matters. This question appears repeatedly in certification exams. Which defect is easier for MFL to detect? Surface or subsurface? Answer. Surface discontinuity. Remember this because it can save you easy marks. We've now covered the physics. Next, we move into one of the most important exam sections. MFL sensors, search coils versus Hall effect sensors. Now we enter one of the highest scoring exam topics in MFL, sensors. Now pay very close attention here. There are two primary MFL sensors. Search coils. Hall effect sensors. This is where many inspectors get confused. Let's start with search coils. Search coils operate based on Faraday's law of electromagnetic induction. That means a voltage is generated only when there is a change in magnetic flux. What does that mean in practical language? If the coil is not moving, no changing flux, no induced voltage, no signal. That is the key. Coils require movement. This question appears repeatedly in certification exams. Which MFL sensor requires movement? Answer: search coil. Now let me show you how this works in the field. Imagine you are scanning a storage tank floor. As the scanner moves across corrosion pits, magnetic flux changes rapidly around the coil. That changing field induces electrical signal. Signal amplitude depends on many factors. Coil movement speed, lift-off distance, coil size, number of turns, orientation to defect. Here's a common mistake I see on site. Inspectors ignore lift-off. Even a small increase in sensor-to-surface distance can dramatically reduce sensitivity. Always control lift-off. Now let's compare coils with Hall effect sensors. Hall effect sensors are completely different. Unlike coils, Hall sensors respond to magnetic field intensity itself. Not field change. Field intensity. That means they can detect static magnetic fields. That is their biggest advantage. Suppose your scanner stops directly over a defect. What happens? Search coil. Signal disappears. Hall sensor still detects the leakage field. That difference is critical. Exam tip. Many Level II candidates answer this incorrectly. Question: what is the major advantage of Hall effect sensors over coils? Correct answer: they do not require movement to detect flux leakage. Now another important detail. Hall elements are extremely thin. About 100 micrometers, or 0.1 millimeter. Remember that number. 100 m. This question appears repeatedly in certification exams. Because they are so thin, Hall sensors are fragile. Here's a field scenario. Suppose you are inspecting corroded tank plates with rough surfaces. If your sensor protection is poor, mechanical impact can damage Hall elements. That means expensive downtime and recalibration. Memory trick. Coil equals change. Hall equals hold. Coil needs changing field. Hall can hold static field. Easy to remember. Now let's build the complete MFL system. Every inspector should visualize this setup clearly. The basic configuration consists of magnetic yoke, 2 magnets with opposing polarity, sensor in the center. Imagine a U-shaped magnetic yoke. At one end you have north polarity. At the other end you have south polarity. Between them sits the sensor. Why opposing polarity? Because opposing poles create a complete magnetic circuit through the test object. That magnetic circuit saturates the material. Now suppose the scanner moves over corrosion. Flux leaks upward. The center sensor detects it. Simple, but powerful. Exam challenge. What is the basic MFL configuration? A common wrong answer is single magnet plus sensor. Incorrect. Correct answer: magnetic yoke bridged across a search coil or sensor. Remember the sensor location. It sits between the magnets. Not outside. Not at one pole. Exactly in the center. Don't memorize this. Understand it. This slide shows the most important industrial application of MFL. Storage tank floor inspection. If you work in refinery shutdowns, you will see this often. Consider an above-ground storage tank inspected under American Petroleum Institute API 653. The tank floor suffers corrosion due to water ingress, soil moisture, sulfur contamination, coating breakdown. Step 1. The scanner moves in a grid pattern. Why a grid? Coverage. Missing even one strip could miss critical corrosion. Step 2. Sensors monitor leakage zones. Areas without leakage usually indicate sound material. Areas with strong leakage suggest metal loss. Step 3. Software converts signals into color maps. Now pay attention to color interpretation. Red. Severe corrosion. Orange. Significant metal loss. Yellow. Moderate loss. Green and blue. Minor or negligible loss. Let me show you real field importance. I have seen tank floors with severe underside pitting where external visual inspection showed nothing. Without MFL, failure would have gone unnoticed. What happens if tank floor corrosion is missed? Leakage. Environmental contamination. Fire hazard. Massive financial loss. This is why MFL is so valuable. Having equipment is not enough. Quality depends on signal quality. The most important quality parameter is signal-to-noise ratio, or SNR. Maximize signal. Minimize noise. 3 major variables affect this. Scanner speed. Too fast. Reduced sensitivity. Missed indications. Too slow. Poor productivity and possible saturation effects. Consistent speed is essential. This is extremely important during refinery shutdown inspections where large scan areas must be completed quickly. Vibration. Surface roughness creates mechanical vibration. That vibration becomes noise. Noise hides defects. This is why scanners use rubber wheels, shock absorbers, damping systems. This question appears repeatedly in certification exams. Why use rubber wheels on MFL scanners? Answer. To reduce vibration-induced noise. Many candidates get trapped here. They think wheels improve mobility only. No. Noise reduction is the real engineering reason. Signal processing. Tiny defect signals must be amplified. But there's danger. High gain also amplifies noise. So modern software uses filtering algorithms. Here's a practical question. Would you trust a scan with poor SNR? Never. Poor SNR means false calls, missed defects, bad inspection decisions. Once a defect is detected, how does the system notify the inspector? 3 common methods. Method 1, automatic stop. When signal exceeds threshold, scanner stops automatically. Advantages. Immediate response. Precise location marking. Limitations. Frequent interruptions. False alarms can waste time. This is common in certain automated systems. Method 2, audible/visual alarm. This method gives continuous alerts. Beep, flashing display, color change. Advantages. Continuous scanning. Fast operator awareness. Limitation. Human attention. Here's a common mistake I see on site. Fatigued inspectors miss alarms. That becomes a serious risk. Method 3, computer software analysis. This is the modern industry standard. The scanner completes the full inspection. Software generates digital maps afterward. Advantages. Full data coverage. Permanent records. Excellent reporting. Best for large tanks. This is the preferred method in large oil and gas facilities. Exam tip. Which notification method is best for large area inspections? Answer. Computer software analysis with color-coded mapping. Field tip. Always document alarm thresholds in the inspection procedure. QA/QC auditors frequently verify this. Missing threshold settings can invalidate your inspection documentation. We have now completed equipment and field application. Next, we move into chapter summary, review questions, and ASNT mock exam. Now we've reached the chapter summary. This is your high-value revision slide. Now pay very close attention here. This slide condenses the entire chapter into core memory points. First, MFL works by magnetizing a test object using either permanent magnets or electric current. Second, it is designed mainly to detect cracks, corrosion, metal loss, but only in ferromagnetic materials. Never forget that limitation. This question appears repeatedly in certification exams. Can MFL inspect aluminum heat exchanger tubing? No. Can MFL inspect carbon steel tank floors? Absolutely. Third, MFL originated from the work of Elmer Sperry in the 1930s. Remember this historical point. Fourth, MFL and MT share magnetic principles. But MT uses particles. MFL uses sensors. This distinction appears repeatedly in ASNT and PCN exams. Fifth, the two major sensors are search coils, Hall effect sensors, memory shortcut, coil moves, Hall stays. Sixth, signal quality depends heavily on speed control, vibration damping, signal filtering. If you understand these 6 ideas, your MFL fundamentals are strong. Don't memorize bullet points. Understand the engineering behind them. Now let's train like real certification candidates. I want you to answer before I reveal each solution. Question 1. What type of discontinuities does MFL seek out? Pause. Think. Many Level II candidates answer this incorrectly. Correct answer. Cracks and corrosion in ferromagnetic materials. Exam trap. Examiners often insert any metal as a distractor. That is wrong. MFL is limited to ferromagnetic materials. Question 2. Which statement about magnetic lines of force is true? This is a favorite exam trap. Some candidates think lines break. Others think lines merge. Both are wrong. Correct answer. Lines never cross, never break, and never merge. They distort around discontinuities. That distortion creates leakage. Remember this because it can save you easy marks. Question 3. What is the basic MFL configuration? Correct answer. A magnetic yoke bridged across a sensor. Simple question. Easy marks. But only if fundamentals are clear. This is why understanding beats memorization. Now we move to rapid-fire review. I want quick answers. No hesitation. Review question 1. Why use large rubber wheels? Answer. To reduce vibration noise. Here's a common mistake I see on site. Inspectors underestimate mechanical noise. Mechanical vibration can hide real corrosion signals. Review question 2. Which 2 sensors are most common? Answer. Search coils and Hall effect sensors. Immediate recall required. Review question 3. Which materials are best for MFL? Answer. Ferromagnetic materials. Not simply magnetic. Use precise technical language. This matters in Level 3 interviews. Review Question 4. What do sensors detect? Answer: magnetic flux leakage. Not broken flux lines. Not merged lines. Leakage caused by distortion. Review Question 5. Major Hall effect advantage? Answer: no movement required. This question appears repeatedly in certification exams. Many candidates wrongly choose more rugged. Wrong. Hall sensors are fragile. Extremely fragile. Remember the thickness. 100 micrometers. Now let's simulate exam pressure. You have 12 minutes in the real mock test. Let's walk through key logic. Question 1. MFL was originally classified under which NDT method? Correct answer: AT. This is a historical trap. Many candidates choose MT. Don't fall for it. Question 2. Who pioneered MFL? Correct answer: Elmer Sperry. Memorize the name. Question 3. As discontinuity depth increases, what happens to leakage signal? Correct answer: it decreases. Why? Because surrounding metal smooths the field distortion. That reduces leakage at the surface. Question 4. Hall effect thickness? Correct answer: 0.1 mm or 100 m. Remember this number. Examiners love numerical details. Question 5. Which sensor detects static leakage fields? Correct answer: Hall effect sensor. Exam tip. If the question contains words like static field, no movement, solid state, think Hall effect immediately. Now this slide is specifically for serious Level 3 candidates. Most inspectors know the theory. Very few understand Level 3 reasoning. Level 3 exams test depth, not memorization. There are 6 critical concepts. 1. Classification history. Why was MFL moved from ET to its own method? Because industrial applications and technology matured. Examiners want reasoning, not just facts. 2. Material applicability. Only ferromagnetic materials. This must be instantly recalled. 3. Flux leakage physics. Understand why leakage forms. If you cannot explain permeability differences between steel and air, your understanding is incomplete. 4. Sensor differentiation. Coils versus Hall sensors. This is a major Level 3 oral exam topic. Be able to compare advantages and limitations. 5. Equipment configuration. Visualize the magnetic circuit. If you cannot sketch it, you don't fully understand it. 6. Quality variables. Speed, vibration, signal processing, SNR. This is extremely important during refinery shutdown inspections. Here's a Level 3 challenge. Suppose your MFL scan shows excessive false calls. What should you investigate first? Think like a Level 3. Possible causes: excessive vibration, poor calibration, bad threshold settings, low SNR. That is the mindset examiners expect. We've reached the end of Chapter 10. Let's finish with rapid revision. Repeat these mentally. MFL method. Magnetization flux leakage sensor detection. Applicable materials. Ferromagnetic only. Origin. 1930s, Elmer Sperry. Primary sensors. Search coil and Hall effect. Basic configuration. Magnetic yoke with opposing polarity magnets and center sensor. Key applications. Wire rope. Pipelines. Tank floors. Tubing. Quality factors. Speed consistency. Vibration control. Signal filtering. Flux rule. Lines never break. Never cross. Never merge. They distort. Depth effect. Deeper discontinuity equals weaker signal. Now before we close, remember this. MFL is one of the fastest growing NDT methods in the oil and gas industry. If you master MFL, you increase your value in tank inspection, pipeline integrity, shutdown projects, corrosion management programs, final exam advice. Focus on these high-frequency traps. ET historical classification. Ferromagnetic only applicability. Hall effect versus coil distinction. 100 m Hall sensor thickness. Flux line behavior. Signal-to-noise ratio. Master these and you will gain easy marks. And more importantly, you'll become a better inspector in the real field. Excellent work completing Chapter 10. Keep training. Keep practicing. And keep thinking like a Level 3 inspector. I'll see you in the next chapter.